Thank you very much. Yes, so I'm Simon Clippingdale. This family name was a present from my father. Thanks, Dad. It won't fit into NHK's system in katakana. So there are several shortened versions of it. Anyway, so I'm at NHK Science and Technology Research Labs, which is, if you know Tokyo, you know maybe that NHK has Hoso Center in Shibuya. Well, this is not there. This is out in Setagayaku, a separate site. So we're going to talk to you about pattern recognition. I'm going to try to keep it simple. I have quite a lot of slides, so to get through them in the time that we have available, I will need to go fairly fast. But don't worry about that because you have copies of the slides, and you don't have to remember every single thing. So, and also you can stop me and ask a question anytime you like. Okay. So after a few introductory comments about what's a pattern and why do you want to recognize it, I've split this into three main areas: feature extraction, pattern classification, and machine learning. I think today, if everything goes fast enough, we will just about start the first part of the pattern classification and then finish off next time. So, what are patterns? In the most general sense, they're any kind of regularities in the data, meaning anything that is not noise. Okay, well, what's the data? Well, it could be discrete or continuous signals of some sort with n-dimensional support. Support is the name given to the independent variable, so functions of space or time. The support is the time or space axis. Examples of which: one-dimensional time series like stock prices or daily temperatures. These tend to be strings of numbers, so they're discrete. Audio waveforms, which tend to be continuous. Electronic signals in general have tended to be one-dimensional. DNA sequence is also a big recent topic for recognition. Increasing the dimensionality of the support, on two-dimensional support we have images, which are a function of, obviously, of two dimensions. Things like surfaces and terrain maps, where a terrain map is a function, the height is a function of two axes. In 3 dimensions, we've got video. We've got 2 dimensions of time and 2 dimensions of space and 1 dimension of time. In 4 dimensions, that covers things like properties of 3-dimensional volumes evolving over time for things like weather forecasting. So those are some examples. Some pictures of some of those. Here's a 1D DNA sequence, a seismogram to try and predict what looks like an earthquake. Might be a pattern recognition application for these. 1D audio waveforms, including music or speech. Here's some 2-dimensional handwriting for OCR is optical character recognition. Recognizing people's signatures is sometimes important for banks and so on. That's Barack Obama there, by the way, in case you want to try copying his signature. Fingerprints, iris, and face recognition are very important for biometrics, which is authenticating who people say they are. Voice print and spectrogram. This is a kind of 2D version where time is along one axis and frequency is up the other, and the brightness expresses the power. Recently, people have looked at using blood vessels in the hand for recognition, so that's another kind of slightly bizarre example. And in 3D, there are things like activity, trying to detect unusual or anomalous activity at airports, for example. Some guy puts a bag down and walks off. That's an anomalous behavior that you want to be able to detect. And another thing that can be used for recognition of people potentially as gait. That's how somebody walks. So there's been some work on that. So those are some of the examples. Some application areas are in coding, recognition and retrieval of text and image and video in general. So coding for transmission of pictures from one place to another, storing video, for example, on a hard disk. If you store it uncompressed, you're going to run out of disk pretty soon. And search as well. You might want to extract particular features to search for. Archive indexing. NHK is quite keen on this because NHK has a lot of video archives of past programs. And right now, if some famous politician dies, for example, and they want to make a news story about it, somebody has to go through the archives and essentially look through all the tapes. So you would like to be able to index your archive so that you can then just do a text search on the index tags. Data mining duplicate detection is an interesting one. Speech recognition for the purposes of creating video subtitles and for text entry and user interface purposes. Written text recognition for mail sorting, recognizing addresses on envelopes. The post office are pretty keen on that. Optical character recognition for turning scanned documents into text. Medical screening and assisted diagnosis is quite an important area in image recognition. And then biometrics and security is probably the biggest area for a lot of this stuff. DNA testing and matching, face and iris and fingerprint and signature and gait and everything else, detection and recognition and verification. These are related but different tasks, and I'll say a bit about what the differences are later on. And abnormal activity detection, like people putting bags down and walking off at the airport. So those are some typical example applications. So to have a look at the first main step in this process, which is feature extraction. I'm going to start with an example, which is channel coding of images. So you want to send an image from place A to place B, or you want to store it on disk or something. So here's a synthetic image, and here's a natural image. And images, as you know, are made up of lots of pixels. And here's the pixel in row I and column J, and here's another one just a bit further along on the same row, K pixels further along. Now the chance, and here are the same pixels in the natural image. Now the chances are, and the closer these pixels are together, statistically it's more likely that the pixel values are going to be closer. And if that's the case, then you're wasting bits if you transmit the value of each pixel over and over and over again independently. So nearby pixel values being generally similar, we don't want to just transmit the whole lot uncompressed. For example, for 8K super high vision uncompressed, you end up with about 48 gigabits per second, which is kind of ridiculous amount of data. You really want to compress that before doing anything with it. So coding is what you do to try to reduce the redundancy in the signal, which is all very well and good. What kind of features should you pull out of the signal to code? In this case, you might think, well, especially for a synthetic image, all the pixel values in this row are actually likely to be identical, so you can just code the pixel value of the first pixel and then say, and another 1,000 or 2,000 the same value. And that's a thing called run length coding, which people actually do. In this case here, there's likely to be a bit more variation as you go along the line here, and a lot of it around here, but you could imagine transmitting an error signal rather than transmitting the actual raw pixel values every time. You could predict the next pixel and just transmit the error instead, which is what normally happens. Anyway, so just a little talk about image processing, because it's a bit difficult, I think, for people to imagine what's going on without a little talk about this. Here's an image, and here's a kind of 5 by 5 pixel patch, f of ij, and here's a filter mask, 5 by 5 pixel mask. And the way that this is traditionally done, linear filtering, this is linear filters, h of ij is these pixel values here. I think this battery is dead. Never mind. We don't have a hardware pointer, do we? Never mind, I'll soldier on with this, and it will slowly die, no doubt. Never mind. So the output at pixel ij, which is this one in the middle, is going to be a sum of the input pixels in this window, each weighted by one of these pixels in the filter mask, and then add the whole lot up. That's definitely dead. Add the whole lot up, and there's your output. And then the output at the next pixel results from shifting this one pixel along, do the same thing again, and repeat until you've got your output image. So that's linear filtering. The reason it's linear is because this only appears as a linear term. There's no f squared or anything like that. So the bigger the input, the bigger the output. So this kind of linear filtering comes from the old days of hardware, when it used to be done with actual electronic components. So the simplest features that people extract from signals are these kind of linear filtered signals. So usually, instead of having all these i's and j's and so on hanging around, we tend to use matrix and vector notation for this kind of thing. So here are our input pixels, and we usually stack them up into a big stack them up into a big vector. This is, I guess you may be familiar with this notation. This is a real n-dimensional vector. Okay, does that work? Nope. Excuse me one moment. Switched on. Okay, all right, we're in business. Okay, so what normally happens here we've got a signal vector, our n pixels from our image, for example. We put it through some kind of a linear transformation, which is a matrix multiplication by this matrix A. T there is a transpose. I guess everyone's happy with that. And the output of this transformation is another feature vector. This is an m-dimensional vector, where m is going to be less than or equal to n here. So there are generally fewer features here than inputs. Not always, but usually in this kind of context. So then we're going to transmit all that stuff over some channel, and at the receiver we have a decoder. That was an encoder. This is a decoder, and we're going to put the signal back together again, or some approximation of it at the other end. So what kind of features are good for doing that? Having represented our data as a real valued n-dimensional vector, like that, in the case of images, you just stack up all the scan lines of pixels into one great big vector. Remove the mean, that tends to be done pretty much always, and then extract m features by this linear transformation A. So here's our output from our transformation. That was the input vector. Take the mean off, do the transformation, and you've got your output. So A here is an n by m matrix. So if that's a square matrix, then the transformation is usually invertible, which means you can, in principle, get your signal back again at the other end if you transmit all the information. And the purpose of doing that might be to treat the different components, these components, differently before reconstructing. You might, for example, assign lots of bits to these components that are important for how the image quality comes out at the other end, and you might not worry about being so accurate with some of the other components that don't affect the image quality so much or are not so visible, for example. So if the number of outputs is less than the number of inputs, then you can't invert the transform. It's a non-invertible or so-called lossy transformation, which sounds bad, but it has the good effect of reducing the dimensionality of the signal, or compressing it, in other words. So you're reducing the amount of data by extracting, hopefully, relevant features from irrelevant data and noise. And one of the good things about doing that is that you don't then waste bits and bytes that you don't need to use transmitting and storing it. So what is a good transformation to use is the question behind feature extraction in this case. So here's an example of a face recognition system. Here's the world with the camera pointing at it, or some part of it. And here we've taken a picture of this guy's face, and we're going to try and recognize him. First, there's a bit of pre-processing and filtering, maybe lining the face up in the image to the center and normalizing the size or whatever. When all that's done, we have a set of features, some features which we will choose for this task. And we're going to combine those maybe as a linear filter or something else with the signal and extract a bunch of features which will again stack up into a vector just like the previous slide. So that will, for this guy's face, when this guy's face is the input, we'll get some output which plotted in this so-called feature space here, it plots as this red dot. In order to find out who this guy is, we have to compare this red dot with some stored data in a database. So in this case, we've just got two people in the database, A and B, and when we plot their features extracted the same way on our feature space, they pan out like this. So looking at where this guy's features have landed in that space, you can see they're kind of surrounded by features from person B, and it's kind of a long way from the nearest feature vector for person A. So the chances are that this is person B, we think. So that's our decision based on our classifier here. So that's a fairly typical system. Leaves the question of what kind of features are good for what kind of tasks. Principal components analysis, or PCA. Now, I don't know, some of you may know this already if you've done any statistics or data analysis. Does anyone already know what this is? Yeah, okay, a few. Okay. So PCA is a classical statistically based method. The idea is to reduce the dimensionality of your signal by extracting features that best express the variation in the signal. So what we're going to do is, given these data vectors, we're going to extract feature vectors, y, from them with some linear transform A. Again, this is as in the previous slides. Subtract the mean first, which is this is an expectation, which is the statistical average of x. I'm going to subtract the mean, do the transformation, and we've got our feature vector. So what's a good transformation to use? Well, it turns out that for our signal X, we can define a thing called a covariance matrix. Sometimes you'll see correlation matrix, sometimes covariance matrix, but they're almost the same thing. And the covariance matrix of our signal Y is this thing. It's the average of the so-called outer product of Y with itself. Essentially, that represents the scattering of examples of Y in this feature space. I'll show you a couple of pictures in a moment. Replacing Y there with this thing, you can express this covariance matrix of Y in terms of the covariance matrix of X, which is this thing in the middle here, plus the transformation matrix A transpose and A at the end. So if we want Y and its covariance matrix to have some useful properties, we can choose the transformation A in the light of the signal properties which are in this covariance matrix of Cx to give us the desired properties in Cy. Specifically, if you set the columns of A to be the top m eigenvectors of the covariance matrix of X in eigenvalue order, if you're not too happy about eigenvectors and eigenvalues, don't worry too much about this. Effectively, what the benefit of doing this is that the covariance matrix of Y, if you choose your transform A like this, turns out to be diagonal, so it's 0 everywhere except the few elements on the diagonal. And what that means is that the components of Y are uncorrelated with each other, and that means that you don't waste bits transmitting redundant correlated information. So the components of Y are not independent, but uncorrelated means, in a very loose sense, independent of each other. So this is the way that you would want to do probably this kind of thing. Another, as well as being uncorrelated, there's another result that you can show, which is that if you transmit only the first few components of Y, this setting A to be this eigenvector transform crams the most of the signal energy possible into the first however many components. So it's efficient from that point of view as well. Okay, in pictures, this is an example where these X's are our input data in 2 dimensions. And if you take the principal components, the eigenvectors of the correlation matrix of this data, they look like this. There's Y1 up there is the biggest one, and Y2 is that way. And these express the spatial scattering of your data in the space. Specifically, the eigenvectors of the correlation matrix are the axes of this subspace. This point in the middle here is the mean of the input data which we take out. And so you can probably see that if you wanted to encode one of these data samples using only one rather than 2 coordinates, the most effective coordinate, the best coordinate that you could use to do that would be this one, because this captures most of the variation in this scatter. Okay, so that's what that looks like. If you wanted to reconstruct your input signal from these eigenvector coefficients, the way you do that, X with a hat is a reconstructed version of X. Put the mean back in and then add, these are the eigenvectors weighted by the components of the Y there. So it's effectively what this amounts to is just a a projection of the input data onto this lower dimensional subspace. I've shown this in 3 dimensions with the subspace in 2 dimensions. If you wanted to encode this 3-dimensional data in using only 2 coordinates, again, this would be the best ones to pick. So mathematically, your reconstruction is the orthogonal projection of your input signal onto the subspace defined by the principal components. Here's an example of a system called an eigenface recognition system. This dates from the early 90s, so it's a bit old now, but people still do use this occasionally. So if you start with a set of training images, these are all aligned to try and get for example, get the eyes and get the mouth in roughly the same place in each image. And this down here is the mean, the average face of all these. So there's the mean. First principal component, if you calculate them, looks like this. You might think, well, what is that? But what it is it expresses the fact that the biggest source of variation between all those images up here is one which makes these parts lighter and this part darker. Similarly, the next biggest principal component makes this area lighter and this whole area darker. So you can probably see that's going to encode hair. And as you go on through the eigenvectors with diminishing all the smaller and smaller and smaller eigenvalues, these get more and more complicated, more and more complex, more and more high frequency, dealing with little details in the data, whereas the first few here are dealing with big details. Okay, so there's one problem potentially with trying to use the eigenvector technique raw, and that is that you need to find the eigenvectors of your data covariance matrix. The problem with that is that this can be a very big matrix. For 128 by 128 pixel images, which is not that big, the correlation matrix, covariance matrix, is this big. And you don't want to be trying to find the eigenvectors of something that big because it will take you all week. So there's a thing you can do whereby instead of computing the eigenvectors of this thing, you can compute the eigenvectors instead of this thing. So the data matrix and its transpose are reversed, and that's much smaller because this is just the number of training images, which could be a few tens. And then having computed the eigenvector decomposition of that, you can recover the eigenvectors of this thing because they're quite simply related. So to put that in context, so we will have a number of registered faces in the database. These are people that you want to recognize. So I've called them R with a K, index K. So what we do is register, for each face image that we want to register in our database, we do the same kind of thing as with the input data. We create a m-dimensional vector like this, yk, of its projection coefficients onto this eigenspace like this. So this is the kth registration, the image that we want to register in the database. This is the coefficient when we take the product of that with the ith eigenvector, the ith member of this series. So having done that, then when a novel face comes along in the input that we want to recognize, first we take the PCA decomposition of that, so I'll call that y dash, in exactly the same way. Take the mean off, do the transformation, and then you can try to recognize this novel input face by, for example, finding the nearest neighbor of its eigenvector coefficient vectors among all these, which are the ones that you've registered in your database. Too many words and not enough pictures. Here's some pictures. So here's the training data that we use to compute the eigenspace in the first place. That may or may not be the same as the set of faces that you want to recognize. If it is, that's probably better, because the eigenspace turns out to be well suited to the images you wish to recognize. Anyhow, so first thing we do is build the eigenspace by doing that keyhole trick to cut down the computation of the amount of computation in computing the eigenspace. Keep only the top m eigenvectors, because as we saw earlier, these get more and more complicated and they represent more and more trivial detail. So the chances are you can actually do your recognition with far fewer than all of these vectors. So we keep only the top few that seem likely to affect the result well. So we compute this eigenspace and the mean image, and then for all the images we want to register in the database, project each of those onto this eigenspace and get this yk thing as projection vector for each face. And then when we want to actually use the system to do recognition, here's a guy's face in the input. Do the same thing again, subtract the mean, project this guy's face onto this eigenspace to give you a vector of coefficients y dash. Compare y dash to all these yks here, which are the ones that you've computed from the database, and get a result, which might be, you might say, well, this guy's going to be the nearest person. I think that guy might be the same guy. Not sure. Or is it this guy? Well, it's that guy there, isn't it? Anyway, you may, in general, of course, your input face won't be exactly the same as one of the pictures in your database. So, but you might find the... Yes?
Can detect anyone who is not in the picture?
Well, you can, what you will be able to do is find the nearest person in the database, or effectively express the input face as a combination of all the faces in the database.
So all the time the output will be someone in the picture?
Well, if you write the software so that that's what it does, yes. You might not. If, for example, this vector is not very near to any of these, then you might say person unknown. So it depends what your application is. And it also depends on what the cost of being wrong is. If you let somebody into a high security place who shouldn't be in there, that's probably bad. So you would probably want to be more cautious in that case. Okay, so that was an example of features, PCA, which are optimal in this kind of statistical sense. But in general, what makes a good feature? You can essentially say that features should be robust, meaning that they should be similar within each class. So one person's face at various angles or various illumination or whatever should ideally not look too different, and should be invariant to likely input transformations, which it would include things like rotations, lighting changes or whatever. They should also be discriminative. That's to say that different people's faces should not give features that are very close together. So here's a good example where our features cluster very nicely. If these all come from person A and these all come from person B, then we have a pretty good shot of discriminating using a fairly simple discriminant. This is not quite so good, but still not bad, where we have multimodal feature space. In this case, we can separate these feature vectors, but we're going to need some kind of non-linear boundary to do it. So that's not quite so simple. Ideally, we would like to use features which make the task of doing this discrimination easier. But you may have to do something like this. And this is bad where they're all mixed up together and you really can't say anything about the input just from where it lands in this feature space. Okay. To put that into more specific terms, using the example of face recognition again, a lot of errors arise from differences between registration and recognition conditions. So you register someone in your database and then they show up at the front door and look into the video camera, but the weather's different, or they're smiling or something, or their hairstyle's different, or they've got sunglasses on. So the difference between these conditions can screw things up. So ideally, the system as a whole should be robust against camera parameter variations. If you change the camera, you still want the thing to work. Or if you take the input video with a different camera from the one that you used to register people. Lighting variations, indoor and outdoor. Outdoor sunlight is horrible, actually, from a recognition point of view, because you get sharp shadows all over people's faces. Aging, if a long time has elapsed since you made your database, people have moved on. Makeup, deformations of the face due to facial expressions, people speaking and moving their face around, hairstyle variation, glasses or not glasses, etc., etc. People wearing hats, facial hair, surgical masks. And 3D head pose is still a difficult thing to get right. Here's an example of why, where here's an input image and we're going to try and match that with images in a database, and you can probably see that the correct person is this one over here. But if you just compare these images at a pixel level in a naive way, this image is more similar to this image at a simple signal level. So what are you going to do about that? So it would be nice to use features that don't suffer from this problem. So what people have done to try and solve that problem is to use combinations of so-called shape and texture, those positional features like where the mouth corners are, how big the nose is, and so on. And luminance features, that's to say, looking at the brightness and shade and color in the image. One rather successful approach was a thing called elastic bunch graph matching, where they defined a fixed set of points on the face. So eyes, nose tip, mouth corners, and so on. And they registered people's faces in the database by computing a load of features at each of those points, and then tried to match by using a so-called elastic grid. Slide this thing around over the face and try and find the place where it matches best. And that worked pretty well. Google bought the company and used this for quite a long time, and these features are still used sometimes. Ideally, the most invariant features to 3D head pose changes like this are 3D shape features. If you could extract a description of the 3D shape of the head, then it wouldn't matter which way your head was pointing. You could rotate this representation in the computer and solve the problem. But that's a lot of computation. You need either stereo cameras to recover 3D shape from a pair of images, or you need to do some kind of shape from motion thing where you effectively use different frames in a video as to do your stereo. And for biometric verification, which means checking that people are who they say they are, features like the iris around the eye, this pattern around the iris, and fingerprints are actually more reliable. The problem with them is that they're more intrusive. You have to get closer to people or physically touch them to get those features. Okay, so here's an example. This is one of the textbooks that I don't know if anyone's bought it, but this is quite old now, but it's still pretty much the best, relatively simple text in pattern recognition. So this example comes from this book, Duda, Hart and Stork. I've called it just DHS in most of these slides. So this is an industrial vision task where we've got some pictures of fish, and we want to classify the fish as salmon or sea bass, given a set of labelled training data. That's images of salmon saying this is salmon, images of sea bass saying this is sea bass. And there's some variation that you have to deal with, including the lighting or the angle that the fish lands on the conveyor and so on. Okay, so for example, you could say, well, we could use the length of the fish. Should be a fairly simple feature to measure with a computer vision system. How does that work out? And the answer is not very well. So salmon, this is the length of the fish in the image along here, and this is the number of images that fit each of these lengths. So here's a histogram. So the lengths of salmon pictures in the training set look like this. Most of them are around this kind of length, but there are quite a few that are much larger. And the sea bass is generally bigger than a salmon, so it's most of the sea bass examples are longer. They're a peak around here somewhere, there's the most probable, but you still have quite a few small ones. Given these histograms, the best performance, if you're going to just try to classify on the basis of length, comes from putting the boundary here. So here's L star. That threshold minimizes the number of errors in this particular case. But all the black salmon examples are above that line, and all the pink sea bass examples this side of that line are going to give you errors. So we've minimized the number of misclassifications, but there are still quite a lot. So this is probably not a really good feature. Okay, well, here's a slightly better one, lightness of scales. Okay, so salmon are darker, sea bass are lighter. So try using that. Here's a histogram of the lightness of salmon scales, lightness of sea bass scales. If you put the boundary here, you do as well as you can with this feature. So it's better, but it's still not that good because there's still some overlap between these histograms down here, which is going to give you errors, assuming that the data is well represented by these histograms. Okay, so, well, how about this then? Use two features, so lightness along here and width or length. I don't know why it's changed to width, but up there. So now if you plot all the salmon examples that you've got and all the sea bass examples that you've got in your training set, it looks like this in 2 dimensions. And you could see from this that actually a decision boundary like this would actually work pretty well. You get fewer errors than using either a vertical line using just the x-axis feature or using a horizontal line. And so if you were just to use this coordinate, project any point onto this line, just reduce the whole thing, you reduce it to 1 coordinate, how far up that line does it fall? You could use that as a single so-called linear discriminant feature, that you could put the threshold about there and say if it falls anywhere up there, then it's probably going to be a sea bass. If it falls anywhere in this half, it's going to be salmon. So that works better, and in general, more dimensions works better than fewer dimensions. So to formalize that a bit, there is a thing called linear discriminant analysis. It's not the same thing as principal component analysis, it should be said. This thing here is not necessarily the biggest principal component of all this data. No, it's not the same thing. The idea is to find the direction, call it V, of a single linear projection, could be like that, could be up here, could be up there, that best separates 2 classes. And this is a pretty extreme example of dimensionality reduction, because you're reducing your whole feature set to 1 dimension in the most extreme case. So here's a couple of 2-dimensional feature spaces with 2 classes of data plotted in them, 2 classes of feature. And here's one candidate for this direction of linear discriminant, and here's another one. And if you project all your data onto this line, well, in this case, you can see that you end up with your data, your projected data is all mixed up. Green, green, blue, green, blue, green, green, blue, green, blue, 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 green, blue, etc. If you project the data onto this line, they cluster pretty nicely. All green down there, all blue up there. So you might think this is a much better direction to project your data on if you're only going to use 1 coordinate. And you'd be right, yes.
How is this different than PCA?
Because in PCA, your principal components express the maximum direction of the amount of variation in your training data, without regard to what class it is. Whereas in the case of LDA, for example, in this case, it looks like the principal component, biggest principal component of this data would probably be in this direction. It's not a very clear example, but in this case, you're looking for one specific direction which maximizes the scatter between the class means, actually, given you want the smallest scatter within each class and the biggest separation between the 2 class means, which is not the same as the criteria that were used in PCA, where you want to use the eigenvectors of the whole data set, the correlation matrix of the whole data set. So you could probably think of examples where they are equivalent, where the biggest principal component is the same as the best projection data, but in general they're not the same.
So
Yeah.
this is not limited to lines, right? Because
Right.
in the case of 3D or 4D,
Yeah.
then
You could project it onto a 2D plane, for example. Yeah, yeah. So just to make it a bit more formal, So you want to maximize the distance between the means of the classes projected onto your line or plane or whatever it might be relative to the scatter. And LDA uses only second order statistics, that's correlation basically, to do this. So what it does is it attempts to maximize this thing, which is called a Rayleigh quotient, as V varies. If you imagine this vector rotating around the origin, you're trying to find the value of V for which this thing is maximum. And where the maths behind it is not really that important, but essentially what you end up with is separation of the projected class means looks like this. Here's our projection direction V, and this SB thing here is between class scatter matrix, which expresses where the class means are in the space. And this thing here is here again is our projection direction V, and this SC thing is a so-called within class scatter matrix for each class. So each class has one of these, and it expresses the scatter, the distribution of, for example, of this class of data, and this class of data will have another different within class scatter matrix. Okay, let's go back to there. There we go. And let's go on to there. So you calculate these two matrices or sets of matrices from your data, and then people tend to use just a sum of the within class scatter matrices from all the classes, and then the task is to maximize this thing up here with respect to V. And you can do that with some matrix calculus. You end up with an eigenvalue problem which can be simplified, and actually that can be simplified further. You don't actually have to solve the eigenvalue problem. You can just note that any multiple of this thing, this is the difference between the two class means, and that is the inverse of the within class scatter matrix. Any multiple of that is a solution. If you want your vector V to be a unit vector, then you just divide it by its length and you've got a unit vector. Okay, so LDA can also be generalized to multiple classes instead of just two, and as you said, it can be generalized to 2 dimensions or more, so long as it's less than the dimensions of the input space. So it fixes the problem that a naively selected projection with widely separated class means may not be best. If you look at these, if you don't consider the scatter within each class, then it kind of looks like the horizontal axis would be best because it gives you a larger separation of the class means than this. But in fact, because of the scatter within each class, it's not the best. And actually this one is better given the shape of the scatter within each class. LDA isn't perfect though, because it will fail if you have cases which are non-Gaussian, that's to say they don't fall into this kind of nice, smooth, elliptic kind of shape, or where the class information itself is in the scatter and the variance rather than the means. Like, for example, in this case, both the class means are right in the middle there, same with these two, and the class information is in the scatter within each class. This thing here, the class means are somewhere up there and somewhere down here, and they don't easily, you can't easily find a line that will split those. Okay, so moving on to modern image features. What kind of features do people actually use? People used to use linear shift invariant features. What that means is going right back to linear filtering. Here we go. Shift invariant means that the values in this filter mask don't change as you scan it across the picture. So your filtering operation is the same everywhere. And that comes from the old days of hardware, where you had physical components that didn't change as you scanned an image through them. Okay, but now more recently, with computational power being better, you can use non-linear features which are more robust to things that you want to be robust to, and can adapt to local image structure, so the filtering can change. The filtering and the features extracted can change from one place to another. That's called non-station. Well, statistically, it's non-stationarity. A lot of image structure is non-stationary because images actually tend to contain textured objects with sharp boundaries, and those sharp boundaries are places where the statistics are very different from region interiors, which are much smoother. And those boundaries tend to be locally one-dimensional. Okay. If you put the word images into Google image search, these are the first few images that come up. And you can see, I think that in most images you've got more or less convex objects with more or less sharp boundaries, and then a load of kind of high frequency texture. So trying to fit the statistics of that kind of pattern is what image features are about. Some classical image features, these are quite old now, but Fourier transforms and wavelet transforms. Does everyone know what a Fourier transform is? No, maybe one or two people, or maybe not. Fourier and wavelet descriptions tend to be frequency based, so they tend to decompose images into low frequency patterns which change slowly, or blurred images if you like, and much higher frequency patterns like these where there's only any signal right at the boundaries. And there are edge detectors which detect exactly these kind of points, followed by on output non-linearities. There are some operators from the sort of late 70s, I guess, onwards, which tend to try and focus on where the signal changes rather than where it stays the same. This is a classic test image. This woman is actually called Lena, and she was a secretary in Sweden in one of the labs where they were doing this work. And this image has become used as a standard test image, which is why you'll see it throughout image processing books and so on. And you can do, for example, horizontal and vertical edge detection, and then combine the outputs to give you a rough idea of where there's some kind of edge going on. You can get a more complicated version by using smaller filters and so on. So these are the kind of features that people used to use. Slightly more modern are so-called Gabor wavelets. These look like this. Here's a pair of Gabor wavelets. And these are complex exponentials, which means they have sine and cosine parts with a kind of Gaussian, smooth Gaussian window. And they have various nice mathematical properties when you're trying to measure aspects of an image. I won't spend too much time on those, but a complete set of these things might look like this. This is the cosine half. You can see they've got positive in the middle and then waves going out. There's also a sine member for each of these. And these things cover if you transform your image into a frequency domain with a Fourier transform, these things cover the frequency domain. So you don't need to worry about that. But those features were used and still are used for some face recognition. In more modern times, particularly for face detection, these so-called Haar wavelets or Haar-like wavelets have been used. And these are very simple features and you can compute them very quickly. It's simply the difference in average luminance between adjacent image rectangles. So in this case, for example, take the average luminance of this white rectangle in the picture of this woman's face, take the average luminance in the black rectangle, subtract them, and that gives you a measure of how much lighter the average pixels are in this rectangle than they are in that rectangle. And the reason this has been very useful for quick face detection is because almost always, relative to this part of the face, the eye area in an image is darker on average. So you can, if the output of this filter is positive, meaning that this area is lighter than this area, then you're in with a chance that it's a face. If not, then you can be pretty certain that the area you're looking at is not a face, so you can discard that immediately and move on to the next candidate area that you're looking at. So the combination of different sizes of these rectangles is very large. It's a vastly over-complete feature set, and the trick is to feed all the results from these many features into a classifier, and the classifier learns which of these features are useful by itself. We'll get around to that in the next lecture. So this was popularized by these Viola and Jones people. If anyone's used the OpenCV computer vision library, the face detector in there, and in a lot of point and click cameras and so on, uses essentially this method. Okay, let's move on. So these things can be computed very quickly. Using a thing called an integral image, you can compute the average pixel brightness over a rectangle in your image, which is unlike the Gabor wavelets with all these waves that need floating point maths. So an integral image, what's that? Well, it's the sum of all the pixels in a rectangle from the top left corner of the image to the pixel where you're at. And the point of computing that is that from any 4 points in that integral image, you can get the average brightness of the pixels in that rectangle very, very fast. All you need is 4 array accesses at the corners once you've computed this integral image. So that's very quick, and that's why these face detectors work much faster than traditional face detectors did. Excuse me. Another popular feature recently is so-called local binary patterns, which are local features expressing local lightness and darkness variations. Essentially, at a given point, you look at how many times the signal in surrounding areas gets lighter and darker as you go around looking at the pixels. Now you can add luminance to all this, so all the numbers get bigger. It doesn't change the feature at all. You can multiply, that's if you shine a light or increase the illumination of your scene, it doesn't change these features, so they're pretty robust. You can learn particular code words that are more common than others and treat all non-uniform patterns, for example, which means that when there's more than 2 transitions as you go around light, dark, those are untypical. You can treat them as a single code word, and it enables you to find salient features rather quickly. I won't go into too much detail because we're going to run out of time if I do. Another one is histograms of oriented gradients. This has been very good and is still used for detecting people's whole bodies. In, for example, self-driving cars use a lot of detectors based on these to try and spot pedestrians wandering around in the road. And these features express a distribution of gradients, light-dark gradients within a neighborhood. These also are invariant to monotonic transformations like addition and multiplication of the luminance, and they also have a bit of room for translation and dilation and rotation of the image. We won't go into the detail of that, but here's an example in pictures. This is from the Dalal and Triggs 2005 paper, which was the main one where this was first published. So this is an average gradient over all the training examples. Their training examples are a load of pictures of people like this. Average gradient looks like that. And these are several orientations of filter computed at each of these cell locations. And then F here, this one here is, these are orientations that seem to contribute. If these are very active, it supports that's evidence for the fact that there might be a person there. So you can see boundary around the head, boundary at the bottom of the shoes, boundaries around the legs and arms. Conversely, if these orientations are active, then that's evidence against the region being a person. Normally, most people don't have a big boundary, lightness, darkness boundary down the middle of them, and they don't have these orientations around the head, perpendicular to the edge of the head. You tend to have orientations parallel to the edge of the head. So this is all used to train a classifier called, you see this SVM here, so support vector machine. Though that's the normal way that these things are used. Okay, moving swiftly on. Another feature that's been popular is so-called scale invariant feature transform, and that was invented by this guy, David Lowe, in Canada, where you do some Gaussian blurring first. This is blurring the image to a number of different extents, and then you take the difference between successive levels of blur and look for maxima and minima in that. Find some key points and the orientations of the signal around them, and create a thing called a key point descriptor. You don't need to worry about the details of all this, but I just thought you should know. A lot of people still use SIFT features. We won't go into the detail here, but suffice to say these descriptors look at large and relatively small regions. In a large region, there's probably more complex stuff going on. In a small region, the approximation is that there's less going on, maybe a single orientation or something. Okay. Scale invariant feature transforms are good for matching, for finding regions in images. For example, here's an image, a target image, and here are some query images taken from a different camera viewpoint, and the idea is to find these 4 locations in this image, and using these SIFT features, you can do that because these features absorb things like the dilation and rotation due to the fact that the camera viewpoint is different here than it is here. And here are the matches for these 4 regions, showing that how the thing has found a number of small image matches and then amalgamated all those matches into matches over these whole regions. Okay, that's enough about image features. We'll just get a bit into pattern classification. We said that the idea of a typical pattern recognition system is to classify a novel input pattern, having extracted features from it. We're going to look at the space of these features and look at where the feature vector that we've extracted lands in the space. Here's that face recognition example again. Here's our feature space, and we're going to try and classify this novel feature vector by where it lands relative to the other training examples in that space. And in order to do that, we need things called decision boundaries, which are locations where we're going to change the output, the verdict of this system. So in this case, you might think that a decision boundary, something like this, would separate most of person A's and person B's training data. But of course, you would like to be a little more rigorous about it. So decision boundaries depend on several things. They depend on the statistical models of the input and the training data, and hopefully the training data resembles the input data statistically, or it's not very good training data. Also depends on performance criteria such as computational cost, the costs of getting it wrong. So misclassifying A as B, for example, misclassifying a person as somebody who's in the database of people allowed into a building might not be the same as classifying, as making the opposite error. So that will all shift your decision boundaries around. So there are several different ways that you can approach this. In decreasing order of complexity, I'm just going to go to the next slide because it illustrates these 3 exemplars, prototypes, and definitions. Here we go. So this is exemplars using training examples. And so here we've got 3 classes, A, B, and C in the training data. Here's a novel input, and we're going to simply classify this as according to the nearest neighbor in the feature space. So in this case, this input is going to get classified as A because A is the nearest training sample to it. Okay, 1NN here means NN means nearest neighbor, by the way. In this case, instead of representing our training data by the data itself, the examples themselves, we represent the data by prototypes, A, B, and C, and we classify the input according to which of the prototypes it's nearest to. That might be the mean of each class of data in the training set, for example. And in this case, the same input is going to get classified as a B. What I've tried to do here is put this big A roughly at the mean position of these 4 training data here. This B is roughly at the mean position of these 4 examples, and this big C is roughly at the mean position of these. And these dotted lines are intended to be the boundaries that are halfway between each pair of letters. So in that case, this input is now going to get classified as class B. Moving on to definition boundaries. In this case, we've got two very simple boundaries here that separate our training sets. One boundary down there separates A from B and C, and one boundary down there separates B from A and C. So here are those two lines, and if we just classify the input as to which region it's in, this time it's going to be a C. So the same input gives you different results in all three cases. So you have to think about what the statistics are of the data and which of these is going to be better. So the exemplars is just using the raw training data, no attempt to model the data, just find the nearest one. Prototypes classify the input against parameters of a discriminative model of the training. For example, modeling each class as centered on its mean with some kind of scatter pattern around it. And the definitions are simple boundaries, things like planes, and classify the input then against parametric data models. Okay. I won't go into the maths of this too much, but it should be, I do have to say that there is a thing called minimum error classification. There is a minimum that's as good as you can do, and it's called Bayes classification. So we were trying to assign an input feature vector X to one of big C classes. This is omega I, so there are C classes, 1 to C. And what we do is define these so-called discriminant functions. So here's our input X. The ith discriminant function is gi of X, and there are going to be big C of these, this number of classes. And you get the minimum error by assigning your input X to that class omega M for which the discriminant function is bigger than any other discriminant function for any other class. Okay, which may seem obvious. I guess it probably is obvious, but a natural choice for this is to set the discriminant function for each class to this thing, which is the conditional probability of omega I given X. So are you familiar with this conditional probability notation? Yeah? Somebody is. Maybe somebody isn't. Okay. So this is the probability that your data X came from class omega I, depending on the value of X. Okay. So it's the posterior probability, meaning that the data is there rather than here. Okay. That the given value of X was from the ith class omega I. Okay, and this follows, there's no point, don't worry about this, but this is just proving that if you set your discriminant functions accordingly, then this will give you the minimum error, and it's called the Bayes error rate, P star. Okay, so that's as good as you can possibly do. There are other discriminant functions that do as well. This is a thing called Bayes rule, which you may know, where this is a posterior probability, the probability that data X came from class omega I. This thing up the top here is the so-called likelihood, which is the probability that of a particular datum X given that it came from omega I, which is not the same thing, and they're related by the prior probabilities of each class omega I and the prior probability of the data itself. But Bayes' rule gives you a way of inverting this to get this, or inverting this to get this. But because the bottom here doesn't matter in this particular application, you can set these discriminant functions instead of setting it to this thing, you can set it to the top of this fraction here, which is the product of the likelihood, which is this thing, and the prior of each class, which is that prior probability of each class. So it may be that you have way more data in some of your training classes than in others. And if that's the case, this is probably going to be bigger in general than for some other I. Okay, so if you do that, that gives you the same ranking. And it's maximum for the same class as setting your discriminant function to this thing, as like we did on the last slide. You can also take the log of this thing. Because log's a monotonic transformation, it doesn't go up and down, it just goes up. The same is true, that you get the same ranking if you take the log of this thing. So doing that gives you this, and it separates the log of the prior from the log of the likelihood there, which is more convenient and makes the prior explicit. So, the decision regions in the feature space are regions within which one of those functions is maximum, within which you're going to assign your input to that particular class. So it's this region of data for which the ith decision region is the region for which the ith discriminant function is bigger than all the others. And any feature vectors that fall in that space are going to be assigned to that class. Okay, so here's an example. This is from Duderhart and Stork again, where we've got two decision regions projected onto this plane at the bottom here. They're R1 and R2. R2 is there and over here. You may wonder why, but that's because this is the likelihood times prior for class 2, and this is the likelihood times prior for class 1, and the likelihood times prior for class 2 is bigger in this red region over here and over here, whereas the likelihood times prior for class 1 is bigger in the middle here and in this kind of pink region here. So projecting that down onto the bottom gives you these decision regions. Okay. So one thing to note about this is that class 2 is the most likely class for data out here, even though the peak of the distribution for class 2 is further away from here than the peak of the distribution for class 1. And that happens because of the combined shape of these two things. Okay, so I don't know if is everyone happy with Gaussian random variables? Possibly not. Here's a probability density function for a Gaussian random variable x, and this just represents the shape of something like this. The most likely value is in the middle. For a Gaussian, that's the mean as well. And the shape of this ellipse, or this ellipse, represents the scatter of the data. In mathematical terms, the scatter of the data within each class is expressed by this thing here. This sigma I is the covariance matrix that we met earlier when we were looking at PCA. So this is the covariance matrix for the ith class. That's the inverse of a covariance matrix. This is the ith class mean being subtracted from our vector x. Here's the same thing again. Take an exponential of that, normalize it by dividing by this thing, and that gives you this kind of classical Gaussian shape. So if we look at the log of this function, log of the prior is just a constant, and the log of this thing is the log of this thing. If you take the log of it, you conveniently get rid of this exponential here, and it gives the discriminant function as this. This thing here is a so-called quadratic form. You've got the inverse of the covariance matrix for the ith class there, and the class mean for the ith class here and here. And this is the main term, which is a quadratic. It's a parabolic term. That does nothing, doesn't change according to the class, so you can ignore that. This does change with the class I, and this reflects how likely each class is individually, the prior probability of each class. So if you've got classes with more training data, more that are just more likely to happen, then this is going to be bigger, and it's going to make your discriminant function bigger as well. Right, we're nearly. I'll just blaze through this final bit, and then we'll leave it for today. Just some examples of what these decision boundaries actually look like for particular types. 3 types of distributions. First one is where the distributions are equal and they're spherical, meaning that all directions are equally probable. So 2 classes have different means, but they have the same shape of distribution. So the covariance matrix in that case is diagonal, and the inverse, in fact, it's not even just diagonal, it's a single number, effectively. The inverse is that. Ignoring terms that don't depend on which class gives you this rather simple discriminant function. This is just a parabolic term, plus this term reflecting the prior here. If all the prior probabilities are equal, then it's even simpler. Then these functions for class I and class J excuse me, are equal to each other at points that are the same distance from the class means. So just look at a picture of that. It looks kind of like this. We've got 2 distributions that are the same with just different means, and sure enough, boundary is a straight line in that case, or a plane or whatever, running right down the middle between the 2 means. The prior, in this case, you might think, well, that line looks like it's shifted over there. This is reflecting the fact that in this example, the prior probability of class 1 is bigger than the prior probability of class 2. Is that right? Yeah, that's right. It shifts the boundary away from class 1 in the direction of class 2. We'll just go back to this bit. Okay, so if you expand this thing, which is this thing from the top of our fraction here, drop the quadratic term, which is this, it just gives you a linear discriminant, which is this thing. So x doesn't appear as the square like in here. It's just a linear function. Okay. So at the decision boundaries, the largest 2 discriminant functions are equal to each other, as we saw on the last slide, and you can write that as this, where this is the 2 class means in question. So this thing is the vector joining one class mean to the other, and x0 here is a point halfway between the 2 class means, shifted according to the difference between the likelihoods, the prior probabilities of the two classes, and it's shifted along this vector which joins the two class means together. So it's if we're in d dimensions, it's a d minus 1 dimensional hyperplane passing through this point that's halfway between the class means shifted according to which class is more likely. So x is the midpoint of the two class means shifted away from the more probable class. Okay. In one dimension, it looks like this. So here's a Gaussian for class 1. Here's the Gaussian, the probability distribution for class 2. But we're going to make the assumption that class 1 is more likely as a prior than class 2, and that shifts this boundary away from the midpoint here towards class 2. In this case, the prior probability of class 1 was 0.7 and class 2 was 0.3. If you go even further, so class 1 is way more likely than class 2, you can actually shift the decision boundary past the peak of class 2 so that your data has to be right up here before you would classify it as class 2. Even if it were to land here, it's still more likely to be class 1 than class 2. Okay. And this is that shown in more dimensions. Same thing in more dimensions. Here's a spherical distribution, here's another spherical distribution, and this plane, this hyperplane that separates the two decision boundaries gets shifted along the axis between the class means according to how likely they are. Okay, so distributions now that are equal but not spherical. I won't go through all the details, but essentially a similar analysis holds, gives the decision boundaries as looking like this, where again this point x0 is point midway between the class means shifted according to their relative prior probabilities along the line between the two class means, but now we've got this factor in here as well. Okay, don't think we need to worry too much about this. Suffice to say the decision boundary, it's a hyperplane again, but it's perpendicular not to the line between the class means, but this thing, which is the line between the class means, tilted by some factor, like this. So here's class 1, class 2. Looked at from the top, they look like this. But now the decision boundary doesn't go down here, which would be the perpendicular to the line between the class means. It's tilted like that because of the shape of these distributions. And given a difference between the prior probabilities, that shifts this thing in this direction. Okay. In a spherical case, here we've got two spherical distributions. Again, the decision boundary now, it's kind of difficult to tell in looking at this particular picture, but the decision boundary now isn't perpendicular to the line between these classes, it's tilted. Last one, arbitrary normal distributions, so they're not necessarily the same shape, they're not necessarily spherical. They can have different covariances in general, and then the discriminant functions become quadratic, and the decision boundaries become so-called hyperquadrics, which look kind of weird in some cases. Here's an example where you've got one spherical distribution and one elongated elliptical one. And here are some others. I won't go through them all, but these are all so-called hyperquadrics, and you can get some quite wacky decision boundaries according to the shapes of your data distributions. Even more wacky ones. And I think that's it. Okay, right. So next thing we're going to do is nearest neighbor classifiers, but we'll do this next week. So that's it for today. If anyone has any questions. Yes.
The last part, the decision, the main idea is to find a discriminant function to decide which, if the features are okay to use.
Yeah, you mean this stuff?
Part, yeah.
The main point of going through this is because a lot of data is either Gaussian or nearly Gaussian, and so you can model quite a lot of data with Gaussian distributions like these. And if you do that, then you'll end up with discriminant boundaries rather like this. So these are the kind of things that get used in practice when the data is modeled as Gaussian.
Okay, so the final is I can have a discrimination boundaries, so I can classify two classes of input.
Or any number of classes.
Any number of classes and any number of features.
Yes, in this case, these examples are kind of low dimensional. These are, this is kind of two-dimensional, but in general you could have much higher dimensions, more features.
Do I need to do feature scaling to go through this?
That depends on how important each of your features is for the discrimination. Certainly, sometimes for things like PCA, you would normalize some of the components, but it depends. It very much depends on what the particular features are that you're using. Also, if you're using completely different types of feature and combining them into one feature vector, some of them might be much bigger, some of the values might be much bigger than others. So you would probably want to normalize those so that the spread is about the same. I mean, the Gaussian modeling will probably do that for you, and it will model any dependencies, any correlations between your features if you're using several features to describe some signal. If you have enough data, training data, you can model any correlations between the components, between the features that you're using.
Any practical example we can you share with us any practical example this is used in, so it's more likely to understand?
Well, quite a lot. A lot of next week we'll look at Gaussian mixture models, which this is a kind of simple example of, and they tend to be used for assigning vectors to one of several Gaussian classes. Now, in practice, people have tried using that for face recognition and other kinds of object recognition. I don't have an example right now of an application where the data is specifically modelled as Gaussian like this, but I'll try and find one for you for next week.
Thank you.
Right.
Page 15, page 18. Page 16.
16.
Yeah. You mentioned that the pictures are from left to right are having more details.
These down here, yeah.
Yeah. Why is that?
Okay, what that is what these are is these are, apart from this one, this is the mean of all the faces. The reason that these get more detailed as you go across is because they're expressing smaller variations in the signal. If we go back to here, this is the direction of the variation. So you might think of that as being like this image. And this is the direction of a smaller variation in the data. And that's like one of these images further down. So it's expressing smaller details. If you pull out the eigenvectors of the correlation matrix of this data, what you'll find is that you can express any of these faces as a combination of the average plus a certain weight times this face plus a certain weight times this face, and so on. And you tend to find that this one expresses more energy. There's more energy in the variation. If you project all of these training faces onto this image, for example, so you're extracting the component from all those images that has a light part here and darker part down here, for example. The energy in that will be bigger than if you project them all onto, say, this one, for example, and this one looks like it's light around the eyelids and dark on the eyebrows, and there's even a light, dark, light thing going on up here. Now, to be honest, that's probably due to poor alignment between these images, rather than being a genuine feature. But it's the reason why they get more detailed is just that there's usually more energy in the lower frequencies. These bigger areas changing have essentially more signal energy. Does that answer your question, though?
I need to think it more. Yeah, thank you.
Okay. Yeah, essentially, looking at this set, I think probably beyond about here, this is almost noise. And actually, you probably find that a system like this would work better if you ignore the last several eigenvectors than if you keep them, because it's not encoding anything that's very important in distinguishing people from each other.
Thank you.
Not sure that I've actually answered your question. I mean, why does it get more detailed? Let me try and answer that again. One reason that it gets more detailed is because these are getting smaller. The actual difference between white and black is these are normalized for display so that the biggest value appears white and the smallest value appears black. And so is this. But actually this image is, the values are quite a bit bigger than this image. So effectively the normalizing so that this fits between full white and full black will make the noise down here bigger. than up here. It's a different way of saying the same thing, but normalizing these images to scaling them so that they fit between black and white is effectively the same thing as stretching this set out here so that you're amplifying the noise in that direction.
So it has nothing to do with the image, actual image. It has just something to do with the, how to say, the location of the image. Is it,
If
if the image comes first, then it will contain more, how to say, energy. And if we put this image later in the location, then it will have more, how to say, noise information.
yeah,
It's just the location of this.
effectively what it is you can express an image and any of those face images as the mean face image plus something times the first eigenface plus something times the second eigenface plus something times the third eigenface. So you have a weighted combination. And you find out that the weights here generally get smaller as the number. If these are in eigenvalue order, what that means is that the weights there are going to get smaller and smaller. So you're dealing with smaller adjustments, like you approximate the face as first this plus however much of this it takes to get to account for the variation between this region and this region or whatever, and then we'll go on adding more and more smaller amounts, smaller and smaller and smaller amounts of these until when you're down to this level, you're really probably not doing anything very useful. So most of these eigen system-based recognition systems tend to use like the top 20 or so eigenvectors. If there are several hundred, we use the top 20 and just ignore the rest because they're not reliable enough. The noise gets bigger.
Thank you.
Pleasure. Any other questions? Not. No plans.
So can we stay?
Yeah. Sure. Sure.
So if you have any questions, so after this class, okay. So I will give some exercise on this week. Okay. So please begin. Okay. So invitation. Okay. Hi. Please thank you very much.
Okay. All right. See.